Hi guys, we are going to talk about electric field in this video. So, as you might recall from earlier in the year, the concept of a field. Fields permeate the entire universe. And they could have a zero value, or they can be disturbed and have waves, like particles, or that we call particles, or they could have a different pattern, as we're going to see here. We can disturb a field permanently, or in an exact mathematical geometric shape that can be represented mathematically. So let's go over the convention of the electric field and how it works. So first, the concept. The concept is this. If I have a positive charge, we'll do a negative charge over here, but let's start with positive. This positive charge will create a disturbance in the electric field. Specifically, to figure out what that disturbance is, we're going to place positive test charges around and see what they do. So if I, one at a time, look at this charge. Obviously the positive here will repel this, so it'll exert a force that points directly away from this central source charge. So we call this the source, we call these the tests. Yes, of course, this will also repel this, but we don't care about what happens to what's causing the field. This will also disturb the field, and this will feel it. This will disturb the field, and this will feel it. So to access what the field looks like, we simply look at what the force looks like, and they are going to be one and the same. The force and the field are intimately connected. So I want these arrows to be approximately the same length, because of course these charges are approximately the same distance away. Beautiful. Let's continue the picture by placing our test charges a little closer. What will the force now look like? Still away. And we'll say this is reduced by a factor of 2 in terms of distance, so it's half as close. Therefore, as you should know, it should be 4 times the force. Remember, this vector is the vector length representing the magnitude of force, and of course with a certain direction. And to complete the picture, let's put the charge twice as far away at varying points in a circle around our source charge, and as you could probably deduce, all of these force vectors will point away and will be a fourth of that. So you want to make sure the vectors point away and their magnitudes represent the force accurately. So I'll just draw these as arrows to save time. This is a mapping of the electric field. The electric field points in the direction of electric force that a positive charge feels. So this positive charge creates a field that at any point in space, so if you pick a random point, say I pick a random point P here, and I ask, what does this electric field look like at point P? Well, I put a positive test charge there, and I ask myself, what does my positive test charge do? It goes away. So at that particular point, the electric field points away. There's a vector that points away, and that vector represents what the force would do. Now the key is there aren't charges everywhere. So I know I draw all these little Q's here. Those don't exist. The only thing that exists is this big Q. So these charges don't exist. The field lines exist. And so what we can do is replace the force with the field. Meaning, instead of writing F in all these places, I can write, we use the capital letter E. So therefore the electric field is 4 times greater because the force is 4 times greater in this inner radius. The electric field is 4 times weaker because the force is 4 times weaker in this outer radius. There you go. Look at that. Look at that transformation from force to field. So the field represents the force, a positive charge field. So they're pretty much the same thing. Field and force are the same thing, except 2 key differences. One is the field only corresponds to positive. In other words, what these positive test charges feel. And the field exists in space without anything else existing there. So there is nothing here, but there is the field. Ooh. So to test what the field looks like, you say, oh, I'm going to pretend there's a positive charge here. What does it do? So let's do that for a negative charge. So the negative source charge, what does its field look like? How does it disturb the field? Well, we put a positive charge here. We put a positive charge here. Positive charge here. At every point, we ask, what would this positive test charge do? Well, this is going to draw in, this is going to be attracted in, this is going to be attracted in, here it'll be attracted in, here it'll be attracted in, here it'll be attracted in. So the electric field at any point in space goes inward. Of course, the farther away you are, it'll be E over 4 if it's twice as far away, because the force is a fourth as large. So the field is the force, and if you're twice as close, it'll be 4 times as large. These will be really large. Oops, that angle was off. And these out here will be really tiny. So as you can see, the field also operates as an inverse square law because the force operates as an inverse square law. Isn't that cool? So the field represents the force. There is nothing here, and the negative charge in the center causes the field to be disturbed such that the field lines here point in, because that's what the force would do. And here the field lines all point out because that's what the force would do. So it's like the field exists, you can't really see it. You can't see the field, so how do you know? Well, you test it. You put a positive charge there, and whatever the positive charge does, that's where the field points. Okay, that's the first concept. Now let's bring some math into it. So let's say that I have a point A, and at point A, the electric field points to the right. And has a value of 40 newtons per coulomb. And I place a let's say I place a positive 1 coulomb charge at A. What is the force? So the force, the electric force, if you know what the electric field is simply the charge at that point. So there doesn't have to be anything at point A. This electric field is created by something else, either over here or over here. So it's either created by a negative charge over here or a positive charge over here. If I put a Q here, I multiply the charge times the field strength, and that gives me the force that it feels. So this field is created by an arrangement of charges, but it's almost like I don't need to know what those charges are, because if I already know the field strength, I can easily calculate the force. So look how intimately field and force are related. It just depends on what charge is feeling the field. Super easy if it's 1 coulomb. Notice how the units work out perfectly. Coulombs times newtons per coulomb gives you newton. There is no special unit for electric field. It's simply force per charge, which is newtons per coulomb, and we have 40 newtons. Question is, what direction? I put a positive charge. Does the positive charge move with the field or against the field? Well, remember, the convention is that a positive charge determines the direction of electric field. So if the electric field points this direction, you can reverse that logic to say the force must point in that direction, because that's how we got the field in the first place. So of course this is going to be 40 newtons to the right. Remember, no positives or negatives, we just want a word description. What about if the charge is negative? So remember to distinguish between what's causing the field and what's feeling the field. Yes, these charges will cause their own field, but two important points. These are extraordinarily important. A charge will never feel its own field. There's another way to look at that. The electric field is independent. Let me reword that. At a specific point. Is independent of what is at that point. For instance, if I place a positive charge here at A, I place this 1 coulomb charge here at A, it doesn't change this value. This value is determined by either a negative charge here or a positive charge here, or both. It's not determined by what is at A, so I can put anything in A. I can put an electron, a proton, a 1 coulomb charge, a negative 1 coulomb charge. I can put whatever I want. The electric field at a specific point is independent of what is at that point. This is enormously important to remember. So if you want to know the electric field at A, you look at what's around it. You never look at what is at A itself. And if I put different things at point A here, it won't change this value of 40. What it will change is the force that this charge feels. The force is definitely dependent on what's at that point. So if I put a negative 1 coulomb charge there, you can plug in a negative sign here if you like. I'd be careful of that though, and I would just think. So the negative sign isn't wrong in this context because you would get negative, which would mean to the left. But for my class, I definitely want you guys to emphasize, and this will help you moving forward. This isn't just me. This will be really helpful to you guys in any context. Emphasize the word. Because positive and negative is kind of arbitrary. So if I have a negative charge, it just experiences a force to the left, which you can certainly look at as a negative force, which is not wrong. So I can even put that there if that helps you. But the negative sign here just means to the left. So just be careful to interpret that properly. Right? So I almost want to erase that. It doesn't look right to me. What looks right to me is 40 newtons to the left. So we can summarize this by saying positive charges. My screen went crazy for a second. Positive charges move with the field. Negative charges move against the field. Or in other words, they do the opposite direction. This is very important to remember, that negative charges always do the opposite of what positive charges do. If I were to place a negative 1 microcoulomb charge at A, the force would be 10 to the negative 6 coulombs times 40 newtons per coulomb, equaling 4 times 10 to the negative 5 newtons to the left. See how easy that is? Super easy. I'm going to do one example of calculating the electric field, so be sure to watch that video. So one more video to watch of calculating the electric field, but this will be enough for this one. Thank you guys so much. I'll see you in class.